This Chapter 2 introduces the various yield measures for bonds, the fundamental pricing equation that relates a bond's price to its yield to maturity, and the limitations of this equation and possible improvements to it. Perhaps the easiest yield measure for a bond is that of current yield. This is simply the coupon divided by the clean price at this moment, or more formally, annualized coupon expressed as a percentage divided by the price expressed as a percentage. This measure is intended to give a more accurate reflection of the return on your investment in the form of the coupon payments when a bond is trading above or below par value especially. So a coupon of 8% paid annually on a bond trading at 80 instead of par results in a current yield of 10%, an entirely intuitive result since you would invest $80 to purchase this bond and would receive $8 per coupon annually. Similarly, if this bond trades at a price of 133.33 relative to par, its current yield would be 6%, another result that should not surprise you, since the coupon of $8 you receive can be visualized as representing $6 on the first 100 of your investment and another $2 on the additional premium of $33.33 that you had to spend in aggregate to purchase this bond. We will, of course, discuss shortly what makes a bond trade at prices different from par. It should take you only a minute to recognize that the relationships described in this table will always hold. When the bond's price is above par, its current yield is less than its coupon. When the bond is priced at par, its current yield equals its coupon. And finally, if the bond is priced below par, its current yield exceeds its coupon. A more difficult concept is that of yield to maturity. Returning to the example of the bond above, with the 8% annual coupon and trading at 80% of par, assume this bond matures in exactly 10 years. Your 10% current yield, while it incorporates to some degree the benefit of purchasing a bond trading at a discount to face value, does not account for the $20 of additional capital gain you will achieve at maturity relative to your initial investment of $80. You can approximate the value of this additional benefit in percentage terms by noting that a gain of $20 spread over 10 years represents a gain of $2 annually, which relative to a purchase price of $80 would amount to an additional 2.5% of yield. So in a sense, this investment represents an opportunity to earn annually over its life a return equal to the sum of the 10% current yield plus this 2.5% of additional return from the capital appreciation, giving an all-in yield to maturity, as it is called, of 12.5%. This would be a reasonable approximation, except for the important inaccuracy of amortizing in effect the $20 capital gain in a linear manner as we did, which ignores the reality that this gain is earned only at maturity and therefore which fails to reflect the time value of money. You should be able to recognize that our simplistic approximation has overstated the all-in yield to maturity, since it has treated the $20 capital gain at maturity as equivalent to an annual cash flow of $2 for 10 years each. And this is obviously not the case. The rate function in Excel allows you to calculate precisely the instrument's yield to maturity, and we will do this in the next worksheet labeled YTM. In column C of this worksheet YTM, we have inserted the bond's total number of periods until maturity in C4. Underneath it, its coupon expressed as a percentage, its price, and of course its face value. We now go to cell C9 and open the dialog box which was inserted in here, revealing the function rate, as you can see on the top left. And we can see that in filling in this dialog box, we have principally relied on cross-references, with the number of period being cross-referenced to cell C4, the payment, i.e. the coupon at the end of each period, being cross-referenced to cell C5 multiplied by the face value appearing in cell C7, the price or present value, PV, being cross-referenced to cell C6, but with, very importantly, a minus sign, because that is the way Excel expects you to input the price for this particular function here. And finally, of course, the face value by cross-referencing cell C7. And upon hitting OK, this bond's yield to maturity is revealed to be 11.46%, which is lower, as anticipated, than our rough estimate earlier of 12.5%. For a bond that pays this 8% coupon semi-annually, but otherwise has all of the same features as the previous bond, you would in fact need to make a number of adjustments in what you insert in the dialog box for rate. Thus, you can see simply by hitting function F2 rather than opening the entire dialog box that once again we have the number of periods, but this time multiplied by 2 to reflect the semi-annual frequency, and therefore the 20 periods instead of 10. After that, we have half the coupon that we previously had, since the payment at the end of each period is now indeed half as large as before. And otherwise we seem to have the same entries, but note this multiply by 2 at the end, which we will discuss in just a moment. And when we hit OK, the yield to maturity turns out to be 11.4%. Had we not multiplied by 2 at the end, the rate would have been the demonstrably false answer of 5.70%. This is demonstrably false if we're calculating the annualized yield to maturity, but in fact, what Excel has done, and the way it's programmed, is to give us here the yield to maturity per period, and therefore since the periods are semi-annual, it becomes appropriate and necessary to multiply by 2, as we had done when we originally opened this cell. This, of course, now appears much more consistent and accurate than what we saw previously, and is much closer to the entry in cell C9. Still, you might continue to be puzzled as to why, despite the more frequent payments of coupons, and therefore the ability to reinvest those coupons and earn additional returns, this yield to maturity for the second bond has turned out to be lower than for the first bond. And the answer is that yield to maturity is itself a sort of nominal interest rate that cannot be used just yet to compare two bonds with different payment frequencies. If we wish to do this, we need one final step, which you may be beginning to anticipate, is to convert the second bond's nominal yield to maturity, as calculated previously, into an effective yield to maturity illustrated in cell C13 by use of our old friend, the function effect. Just to check on this, we open this particular function here and indeed notice that we appear to have converted the 1140 from cell C11 into an effective yield to maturity of 1173 when taking into account the semi-annual payment frequency and therefore the ability to reinvest. At this point, the 1173 does seem quite rightly in line with and higher as expected than the 1146 that applied to the bond with the same coupon but with the only annual payment frequency. We recognize that all this, and in particular these various subtle distinctions between nominal yield, effective yield, nominal yield to maturity, and effective yield to maturity, can be quite confusing, and therefore we advise you to review this section very carefully if your work requires detailed familiarity with bond pricing and trading. The rate function in Excel works very nicely, but assumes the calculation of yield to maturity generally takes place on a coupon payment date, since you're allowed to enter only a whole number for the number of periods. We illustrate next what you should do if you need to do this calculation on any other day by means of this worksheet YTM2. Assume the bond with the semi-annual 8% coupon matures on May 31, 2019, and that today is July 31, 2009, therefore 2 months into the interest period. This worksheet, as you can see, begins by inserting the settlement date and the maturity date, described in Excel as the settlement date and the maturity date, at the top of this worksheet, before adding underneath the coupon, the face value, the price, and of course the semi-annual frequency of coupon payment dates. We generally advise that you not try to type in the dates, but instead to rely on Excel operator date, which, as you can see, works simply by writing equals date and then inserting the year, comma, the month, comma, and the date, or perhaps more easily seen by opening the function wizard here And the reason for recommending this function is that it avoids, in particular, any ambiguity between American and European dates, and therefore the order of the month and the day. Moving now to cell C11, we open Excel operator here, yield, different from rate that we previously used. And we proceed to fill in, again via cross-references to the entries in column C, these various spaces, including for the settlement date, C4, the maturity date, cross-referencing cell C5, which you can see are the correct references, the coupon rate, cross-referencing C6, the price, only this time for this function in Excel you do not put it in as a negative but keep it as a positive, the redemption value, i.e. the face value, cross-referencing C8, and finally the frequency, hiding here but cross-referencing cell C9. A few things of importance to note here are the following. First, as we have mentioned, in the yield operator, we always insert the price as a positive and not as a negative. This is quite simply the way Excel has chosen to program its various functions. There is nothing you can do about this except to make sure you do not forget it for the rest of your career. Second, Excel uses the term redemption to refer to the bond's face value, which is intuitive enough. Third, please note that the coupon is inserted as 8% in this example without dividing it by the number 2, since a separate part of the dialog box, and specifically this one here, asks you to insert the frequency and will reflect it automatically in the calculation. And finally, the last entry that we left blank here in the dialog box asks you for the bond's basis, which is nothing more than the day count convention that we had discussed in chapter 1. And this now becomes relevant since here we are no longer standing on an exact coupon payment date. For the time being, we leave this item blank, but we'll return to it shortly. Upon hitting OK, the bond's yield to maturity appears as 11.44%, slightly higher than our 11.40% on the previous worksheet, which is not surprising since 2 months have lapsed since the last coupon, but the bond's price has remained 80, so the receipt of the same remaining cash flows as before, but over a slightly shorter time period, rightly bumps up your all-in return. We remind you once again, however, that this 1144 is only a nominal rate, and that to compare it to that of any other bond, especially a bond with a different frequency, would require you to turn it first into an effective annual equivalent. With respect to the entry in the dialog box for the bond's basis or day count convention, we hit the help function on the bottom left of the dialog box to learn more about this. And here it is. After scrolling down a little bit in the help function, find that Excel allows us 1 out of 5 alternatives, some of which are the same ones as we had described in Chapter 1, including actual and actual 360 and 360, but please note Excel offering us a European and the US alternative to that 360 convention. By leaving this item blank as we did previously, Excel, as always, assumes the value 0, which corresponds, as you can see, to what is known as the European, the US 30360 NASD convention, National Association of Securities Dealers. Had we chosen 1, this would have put us in an actual convention, and so on. We remind you again that there are many more conventions around the world than these 5. Yield to maturity is perhaps the metric most commonly used to enable a comparison of two bonds that have the same maturity but different coupons and or prices. To illustrate, we take bonds A and B with the terms set forth in this worksheet comparison. For now, we assume they both have a semi-annual payment frequency as indicated in this row 10. You should recognize the need for this comparison between these two bonds. The higher coupon of 5% paid by bond A versus 4% by bond B is presumably offset to some degree by bond A's substantially higher price than bond B's, making a direct comparison of these two bonds difficult. In effect, the question boils down to whether the $9 additionally paid to purchase bond A represents greater or lesser value on a PV basis than the additional 1% coupon this bond delivers annually, which aggregate to $10 over the bond's life. This comparison is tricky because it needs to reflect the time value of money and the different entry prices under the two bonds. Yield to maturity provides a reasonable basis for this comparison. Moving down to row 12 and using the rate operator as before, multiplied by 2, please remember at the end, given the semi-annual payment frequency, we see that bond A's yield to maturity comes to 438, which lags bond B's yield to maturity of 450 by some 12 basis points. Assuming you perceive no differences in the two bonds' credit quality, liquidity, or other factors that might explain this difference, you would obviously be tempted to purchase bond B rather than bond A. Our module on pricing default swaps provides a reasonably comprehensive list of what some of these other factors might be. We hope we have done a decent job explaining yield to maturity in relatively non-technical terms, but for specialists we must now provide a more formal definition. We remind you first that any future cash flow has a present value equal to its size, discounted to the present time via an appropriate discounting operation. Specifically for our 10-year bond paying an annual coupon of 8% and priced at 80, a moment's thought should confirm that the above observation can be summarized in formal notation as follows. Price equals the first coupon of 8 discounted at 1 plus y plus the second coupon of 8 discounted at 1 plus y squared, and so on. And in particular, you should please note the numerator of 108 in the last term, which reflects the sum of the last coupon plus the principal. Quite simply, the value of y that satisfies this equation is what we define as the bond's yield to maturity. It is the single rate which, when inserted into each denominator as the discounting rate for each cash flow, raised to the appropriate power, of course, brings the bond's price under the formula in line with its observed price in the marketplace. If another bond pays a coupon of 8% semi-annually, but otherwise has the same terms, the above formula needs to be rewritten as follows. Once again, with the price equal to each cash flow, but this time the cash flow is being $4, discounted at 1 plus y over 2, reflecting the semi-annual frequency, and so on, squaring and then cubing the denominator, and of course leaving the final numerator this time to be 104 and the final denominator to be 1 plus y over 2 to the power 20. The Excel operator rate, which we used previously for this bond, solves for the entire term y over 2 in the above equation. And this explains why in Excel we were required to multiply by 2 at the end to derive the annualized yield to maturity. In effect, the rate operator in Excel calculates a yield to maturity for the period falling between two coupons, and leaves you with the task of then multiplying by the payment frequency to derive the annualized yield to maturity quoted in the normal method. And as noted previously, this operator rate does nothing to convert yield to maturity into an effective rate, which you then must do if you wish to do it via the effect operator should you be comparing two bonds with different frequencies. We can now write the above formula in its most general form. Thus, for a bond having a maturity of n years, a payment frequency of F as in franc, a coupon of C dollars per $100 of face value on each coupon payment date, and the price of PR, we can write price equals, and then again each coupon discounted at 1 plus y over the frequency raised to some appropriate power, and not to forget with the last term to include in the numerator the principal of 100. A glance at the formula above should lead you to the following observations. First, for a given bond and a given coupon, as the bond's price rises, its yield to maturity falls, and vice versa. Second, if a bond is trading above par, its yield to maturity is lower than its coupon, and vice versa if it is trading at a discount to par. And third, if two bonds are trading at the same discount to par and have the same coupon and the same payment frequency, the one with the longer maturity will have the lower yield to maturity, and vice versa if the two bonds are trading at the same premium to par. It turns out that our earlier table can be expanded as follows. For bonds whose price is above par, yield to maturity is below current yield, which is below the coupon. For bonds priced at par, all of yield to maturity, current yield, and coupon are exactly equal. And finally, for bonds trading below par, the greater of these three is the yield to maturity, followed by the current yield, and followed last by coupon. You should spend the time confirming all of these observations in an Excel worksheet if you do not find them intuitive from the formula. Yield to maturity is certainly a useful and relatively simple tool for comparing the all-in return from two bonds that have the same tenor. But it suffers in one important respect from this very simplicity. You will recall that in the formula defining yield to maturity, which is about to be reproduced here for your convenience, we used the same single value for y in each denominator, adjusting for the difference in the time of occurrence of each cash flow only by raising each denominator to a different power. And yet, the use of the same discounting rate in the denominator, or specifically the same value of y, suggests in effect a flat yield curve, which is almost never the case. A more correct approach would be to use gradually increasing values for the discounting rate y when the curve is upward sloping, and gradually decreasing values when the curve is inverted. The problem, of course, would then be that our single equation would contain several variables and so would have an infinite number of solutions. For this reason, the convention has been adopted to use a single value for all discounting rates, despite the obvious limitations of this approach. In more advanced modules, we will discuss more sophisticated approaches that use the individual risk-free rate in the denominator for each particular cash flow date, and then add to that a credit spread of some kind that makes the sum of the PVs of all cash flows equal to the bond's observed price. Then the yield measure, for purposes of comparing two bonds, really then becomes this credit spread, since the same risk-free discounting rate would be used for any cash flow under any bond occurring on that same date. We complete this discussion of yield to maturity by introducing the closely related concept of yield to call. Return to the bond we saw previously with the 8% annual coupon, 10-year maturity, and price of 80, and assume that this bond may be called, i.e. prepaid, by the issuer 5 years before its maturity date at par. The holder should normally be quite pleased to have the issuer call the bond on its call date, since the $20 discount to par would be earned under this scenario, after only 5 years instead of the anticipated 10, providing a significant boost to the total return for the holding period. We should therefore expect to calculate, in the case of a call of this bond, a significantly higher return for the investor than the 11.44% that we previously calculated over the 10-year holding period. Yield to call as a concept measures quite simply the bond's yield to maturity, assuming, however, that the bond is indeed called on its call date, and otherwise works exactly like yield to maturity, except, of course, that the number of periods remaining until the call date now replaces the number of periods until maturity. This worksheet YTC lays out the bond's features just as before, but this time in the dialog box for the operator rate, we replace the entry for the first item with a cross-reference to cell C8 instead of cell C7, this being therefore the call date after 5 years instead of the maturity date after 10 years, and thereby obtain a yield to call of 13.8%, consistent with our intuition of a higher anticipated yield. Two more important observations are needed regarding yield to call. First, an issuer is often required to pay premium over par if he decides to call a bond prior to maturity, which of course increases the return to the investor versus a call at par. If this is the case, you should insert in the rate operator the full call price instead of just 100 when deriving the yield to call. Second, most callable bonds may be called on several alternative call dates rather than on just one date. This means that we can calculate for such a bond, as listed here, a yield to first call, a yield to second call, yield to third call, and so on, which will usually all be different from one another. And some people therefore use the notion of yield to worst to describe the lowest yield to call calculated for any of these call dates. This completes our discussion of bond yield measures as well as the price-yield relationship, and brings us to the end of this chapter 2.